Thank you very much to all of you that are coming to this meeting. Unfortunately, this is a team meeting, not face-to-face, which I'd like it more. But next time we will do it face-to-face. This is my own town, Haifa, as you can see. And we will start talking about contact lens innovation. Leonardo da Vinci, the great Italian inventor, just scripted the first contact lens, and we have it for more than 800 years. But on September 1947, Joseph Pascal has a radical innovation in contact lenses. And this was the starting point of the real contact lens base of what we are knowing now. It was based on this type of lenses. Of course, it was a PMMA lens, not glass lens like Leonardo da Vinci, but they started then the innovation of a contact lens. When we are talking about time, as I said, the 1940s, it was starting making contact lenses from plastic. 1950s, they developed the first hydrogel lens. 1918, 30 years later, starting the manufacturing of the frequent replacement program system lenses for weekly, monthly, and something like this. By this time, all of the lenses were based on annual uses. 1990s, the lenses, the contact lenses has been more user-friendly, very easy to install them on the eye, take them out, clean them, and the variation of parameters was almost unlimited. Of course, it was a developing starting point of the manufacturing systems, the CNC machines. Going back to the 2000s decade, where the silicone hydrogel contact lenses has started with, of course, the high oxygen permeability, the high decay, what we call. And on 2008, we started the one-day disposable lenses, which make a huge revolution in the field of contact lenses. Today, we are standing with more than 160 contact lens brands designed to address a range vision health needs, from lenses to reshape the world, like overnight lenses, through lenses with UV blocking, lenses for presbyopics, and lenses that can even correct or added lenses for color blinds. And for the future, we are looking for this decade, which we just started a few months ago, to continuing innovations in order to make a better comfort, a more wearing time, a better or easier handling, less cost, and of course, better vision. All of this we are doing with designs, materials, and manufacturing process. There is a say, I've been last on January, before we get into this mess now, I've been to the GSLS seminar in Las Vegas, and they said over there that contact lenses are among the fastest progressing topics in optometry. When we talk about one with the scleral lenses that can correct many types of irregulation of corneas, dryness, myopia management like the CRT, the autokeratology, and special soft lenses like the myopia and the MySight, CooperVision MySight. Like sensitive contact lenses like Oasis with translation, therapeutics, and multifocal. When we talk about optical, about design, we talk about optimized lenses for distance, and all distances focus with multifocal. Special techniques application to earned ocular wavefront tomography to design contact lenses optic in order to correct off-axis wavefront aberration. We will talk about this later. We talk about materials that we can improve, for example, the lens thickness, the wettability, which is very, very important, the oxygen permeability, water content, and the mechanical properties. If we are taking into account, for example, the CooperVision My Day lens, it made by a smart silicone. The chemical engineers success reducing the amount of silicone to third, but they left the decay over T over 100, with, of course, the better wettability. Silicone is oil, and oil and water cannot go together. This is why the most problematic issue with silicone hydrogel lenses is the wettability. As I said, the CooperVision chemical engineers reduce the amount of silicone without worse in other parameters like the decay. Another issue which is very, very important is the biocompatible that take low deposition of tears components, eliminate end of the day discomfort, develop biomaterials for applications such as drug delivery, temperature and pH responsive, like we will talk later. Liquid crystal contact lenses for presbyopia allow to alter the lens power in the region of about +2 diopter, which is very, very important. When we talk about manufacturing, reverse geometry option, tailor-made manufacturing wavefront option means to take the information from the machine that give us the information about the wavefront and to edit this to the lathe machine in order to make the best fitting, optic fitting to the patient. Means we are doing a tailor-made optic. And we have to meet new materials with new manufacturing demands. And above all this, we are still doing the Snellen chart in order to analyze the vision. We have to produce, to develop new machines in order to check our vision in three-dimension inspection, in other issues. And the last innovation should come in the contact lens solution. Antibacterial silver impregnation coating for lens case, which reduce the amount of sites on the lens case to minimum, to 0, and super liquid deposition for silicone hydrogel lenses. And in summary, we are using contact lenses for more than 50 years. For the next few decades, we'll see a considerable broadening of the range of applications for contact lenses. Treatment platform for myopic progression, autokeratology or spacious soft lenses, new material, ocular drug delivery, and biosensors. Smart contact lenses. MEMS means micro electromechanical system. Every year, components get smaller, what we call Bell's law. Now, having batteries, antennas, LEDs, mechanical, electronic sensor, small enough and low cost enough to be put in contact lenses. The nanotechnology, components for modulate drug delivery, light filtering, spatial, spectral and polarizing, and micro-optical elements, diamond turning and molding to sub-micro accuracy. When we talk about the Bell's law, we see that in the 1960s, a computer was holding, let's say, one or two big rooms. And then when we get into 2020, in all our mobiles, we have a computer that is stronger than this on the mainframe in thousand, but smaller in micrometer, the size of these components. So every decade, we are decreasing in volume in 100 and 10 times more stronger in the options of calculating. When we look at this picture, the intralens components as light emitting power sources, and it is in red because we will talk about this later, sensor, processors, antenna, oxygen generators, micro-optical components like lenslets, filters, reflector, deflectors, diffusions, nanostructures like drug delivery and antimicrobial products and systems. Sensing and controlling a non-invasive diagnostic device. Intraocular pressure sensing, it's a nanosensor fabricated in silicon-based MEMS technology, measure corneal shape change related to IOP, and for the future, couple with drug delivery means that immediately when we check that there is a problem in the intraocular pressure, immediately the lens will release drug in order to fix it. When we talk about this component, there is a huge picture here of this component that can do everything in 1.5 millimeter cube. So it has all the needs to check the IOP. It has even a thin film lithium battery, and everything with, that we need in order to check the IOP. This is another IOP sensing the intraocular pressure with a conductive silver wires used to measure pressure change. Another sensor is blood sugar sensors, which can do about the same what previous does in order to send us information to put the medication not through the eye, through another issue. But the idea is that there is an antenna that will send the information about the situation, the level of the sugar in the blood. Another innovation sensor is from Google and Novartis. Google is a microelectronic technology, Novartis regarding to medication. They build a biosensing contact lens that measuring the level of the blood glucose in the scleration of the eye and transmitting this information to the patient mobile device. From this place, this device can do everything, because we know that we have a system that can send a medication to the patient that are implanted to the body. Another lens is sensitive to the concentration of these elements, and immediately when there is any disease of dryness, for example, that raise one, they change the pH, for example, immediately you can see it on the lens and to analyze it. The doctor can put this lens to the patient and immediately to analyze the problem by the color of what you can see. The drug delivery. When we see this graph, we can see in orange, when we put a drop, maximum solution is getting into the eye, most of it goes out, and the effectiveness is in a very, very, very small time. So immediately these tears, this drop of tears can work for, let's say, 1 hour, 1.5 hours, not more. When we talk about just a contact lens that we put in a medication together with saline, and we put it on the eye, we get a slow release of this medication. Immediately, we get the higher level of efficiency, but it takes something like 10 hours, the time we are taking out the lens, for example, the effectiveness of this medication. Of course, it going low and low and low because it mixed with the tears. When we take a drug delivery contact lens that was designed for this with the system, how it works, how the drug is connected to the matrician of the soft lens, we can get a very nice effectiveness of the medication, of the medicine, along the time. So we can use this lens for many hours, and to get, if we need high demand of medication, we can get it in very, very small amount, direct to the eye, and the cure will be very fast. These smart lenses, as we saw in the last graph, these smart lenses are capable of sensing changes in the interocular pressure, monitoring the prognosis of glaucoma and its treatment progress. The drug mechanism, we can see it in the next slide. This is the lens on the cornea, of course, on the eye. And there is a combination of a drug loaded into the body of the lens, connected in such a way to the material, and when there is a need for drug, it will release it, of course, toward the cornea because of the difference of pressure between the outside to the lens and the lens to the cornea. So the direction will be for sure from outside in. So the drug will touch the cornea and affect the cornea. Another issue is a telescopic contact lens zoom with a wick of the eye. Means that if we are taking this lens and we blink, let's say once or twice, fast twice, it will show us a 2.8 bigger image than in normal in normal view. We can see here the design of the lens. It's just the optic design of the lens. So when we doesn't blink or blink normal, the vision will be to the center of the lens and the center of the cornea. And when we blink twice, it will move the light toward to a magnifier and will show us a bigger view, like we can see in this slide. This is the normal view. We can see here, this is the normal view. The idea is that we have 80 degrees field of vision, and we take just 20 degrees field of vision and we zoom it to enlarge the target. One of the biggest innovation that I believe will be by 2025, it is the media, the wearable computing. The idea is that we will have all the information that we need on our eyes immediately. So we can think of something, we can look at something, and immediately it will say us where we have to go, if we are in the right place, or what is this, or look at the person, and maybe it will give us his name. The idea is that when we take all the previous solution for this, I know that we are dealing with this for more than 10 years in the field of contact lenses, and the most problematic issue was to get to a bigger field of vision without doing nothing to our vision, to give all the information. One of the breakthrough of this idea was the optic contact lens. It was built on the Paragon normal eyes, which was a 15.5 mini-sclera platform. The outer lens provide normal vision for real world, and the center lens streamed a high definition in 3 dimensions digital media for eyewear. Paragon Vision Science is also now a part of CooperVision. But one of the problems with this, that it should as a glasses that supply the power, that supplies the images, and the idea is that we should have an added an added instrument to work it out. The last innovation in this is the module lens, which is the brand new system. And it has a built-in display, which means that we have only the contact lens for the smart media contact lens. And it is the first true smart contact lens. Images and text in your eye for medical purposes and for everything. It is an invisible breakthrough. This is the idea of the lens. It has some layers which give us all the needs we need as contact lenses from one point of view, and the display, the micro display from the other point of view, and of course all the smart software that we should need for this contact lens. And it is for future patient, people that like to play 3 dimensions gaming like we have today with a lot of masks and everything. They should do it only with these contact lenses. Medical and surgical system. Look, the surgical can wear those lenses immediately, can have information from other machines according to the operation that he's doing, for low vision, for defense training and simulation, and for defense and intelligent field operation. The soldier will use this with these contact lenses to get real-time information and picture from the big field, and from, let's say, from intelligence and everything. And when we talk about optics, we must maintain optical integrity so much the more in every other way. We will demand simulators, vision lens, correct for multifocal, for example, correct all sphere and cylinder, center over the visual axis, produce excellent optics. Means that we need a tool that allowed us tailor-made lenses in low price, of course, to allow us to manufacture lenses for the best demands that we need. We don't want compromised. The machines that will be in the market will be the Optoform 80. We are working in our company, we are working with the Optoform series. We have the latest Optoform 40, which they have a fast tool servo, which is this instrument here that allowed us to work in 3 dimensions. And this lens will be polish-free, means that we don't have to polish the surface of the lens in order to get the best optic. The idea is that we can manufacture with this machine, with these elements here, the best lenses, the best design, and the best optic. We have to take care when we design lenses, we have to take care that, for example, soft lenses are deformed on the cornea, when we put a symmetrical soft lens, it is deformed on the cornea because the cornea, for example, has a nasal and temporal not the same. For example, we have astigmatism, small astigmatism, that the lens is riding down on this astigmatism. We have to take care of the pupil size and reactivity. We have to take care of the lens location, the centration, and the visual axis location, and the corneal power spread. In multifocal lenses, it is essential. So when we talk about smart lenses for presbyopia, I believe that this decade, most of the contact lens manufacturers will concentrate in doing the presbyopia lenses, the multifocal or bifocal contact lenses, the best as they can, because I believe that we are now in the third generations of contact lenses, and all the people that starting 20 years ago, when they were 20, 25, they will now going into the age of presbyopia, and we have to give them the best product. Here is, for example, a smart lens that energize fluid meniscus to the patient's need, for example. So we can see it here that we have plus power, the addition, when the patient is reading, or we have minus when he's looking toward the far. So this is something, this is a special lens that will affect the meniscus of the lens, will remove water or just other liquid from center to the periphery, or vice versa. In order, when it goes to the periphery, it will make a minus lens. When it goes into the center, it will make a plus lens. For example, if we need plus 1.5 diopter addition or plus 2 diopter addition. Of course, this should affect in microseconds. In milliseconds, it also will be okay. Another idea is taking from the eyes of fishes and other animals living in rivers with a lot of mud. So they have to see in close vision when they are underwater. So the idea is to change the design of the lens regarding to the needs of they just try to copy the eye of these animals in order to do the lens for reading, for the near sight. When we would like to make smart lenses, we have to make to analyze the shape of the optic on the eye. I'm not talking about just the shape of the cornea, which is a part of it, but when we talk about optic, we have to do the wave front detected in order to analyze our need. And this is just an example. So we can measure the eye order aberration of the patient to analyze it, okay, and to make a lens, to design a lens. This is, for example, with no lens. This is the eye from normal lens, and we take to the account this spherical aberration, we can do a very nice, to manufacture a very nice lens optic with no aberrations. Okay, if you see the colors is between 0 and 0.1, minus 0.1. When we are talking about this lens, for example, this solution, we are talking from 0.7 to 0. Okay, so it is a much higher aberration on this solution. But one of the other issue when we talk about design a lens to multifocal, we find out the most of the problems are because of the centration and rotation of the lenses. For example, if we are looking about this sketch and we talk about the red cross is the center of the eye. Okay, this is the pupil. But the center of the lens is about 0.5 of a millimeter in X, and it is not at the same place. More of this, there is a rotation of the lens of about 10 degrees, nasal rotation. So we have to take care of all of this information. We are doing the wavefront analysis, and we put it to the computer that will allow us to manufacture the lens in order to correct this deformation. This is one thing that is very important when we are talking about doing multifocal lenses, because centration is very important. We know that in some other lenses, centration like autokeratology, centration is essential, but here it's a necessary. We are looking for lenses that will do light therapy. For example, we can see here that the lighting condition doesn't allow us to see the information, for example, as this is without contact lenses. And when we put a contact lens, the smart contact lens know exactly what to do in order to see the whole picture. Okay, we can see this is by day, and this is the same picture by night. Another issue is to control the spectrum of the light that we need in order to get a better vision. So the lens has autofocus, auto filters that can play with the light and to analyze like a Photoshop, like we're doing in a Photoshop, to improve the vision that we can see, the picture that we can see with this contact lens, which means like putting a yellow filter in order to see better in a fog, for example, or something like this. But when we talk about smart contact lenses, the most problematic issue is energy, because we know that supplying or putting battery, even so the battery can reload from day to day. We will find a way to reload the battery. It is a huge problem. We have to look for auto energy supply for these smart contact lenses. And there is an Israeli startup that they find an idea, that they are working on an idea to supply continuous energy, self-energy to the contact lens. Even so, you have to wear this lens 24/7. So if we're talking about accommodating IOL, or we're talking about smart contact lenses, we're talking about just other applications, we need, for all of this, we need the power. The system that we have today in order is inductive coupling. Like today we are reload our mobile phone. We put the mobile on a plate, and there is a system that can recharge it. There is an optical charging. We have RF charging, and we have ultrasonic transducers. But all of these instruments need to work to be by the side of these contact lenses, because the contact lens itself cannot work for more than, let's say, a few hours a day in continuous work. And if we need for a blood sugar sensor or other sensor, we want it to be 24/7 to work automatically on us. So the idea is to make a system that will give us ultra low energy harvesting. Those instruments, those chips that are on the smart contact lenses need a very, very small amount of power. So we find out, or they found out, that the blinking 18,000 times per day, the eye movement, will give us 24/7 energy harvesting. And they have a very nice graph that shows the amount of power that they get from this system. The idea is, the technology is to use like a alternator, to use the movement of the eyelid. They put something on the eyelid. We can see it here, the eyelid patch. And there is the smart contact lens that give us the power, or gets the power from the movement of the eyelid. And this small capacitor, for example, or something like this, will supply the power to all the rest of the electronics that will be on this contact lens. The idea is to supply just the technology to supply 24/7 power. So this is a one-stop solution, especially for medical solutions. These are references, and thank you very, very much, and hope that I could meet you all very soon face to face. Thank you.